In this video, I'm going to go through some of the problems from the Rational Expressions Review 2 worksheet. So for number 1, state the values of x for which the following is undefined. Remember, a fraction is undefined anytime the denominator is equal to 0, right? Because we can't divide by 0. So I really don't even care what the numerator looks like. All I need to do is consider when x squared plus 2x minus 8 is equal to 0. Now this is a nice quadratic because the highest power of x I see is 2, and the strategy is get one side equal to 0, which I already did, and factor. This looks like a regular AM method because the leading coefficient's 1. So I would just ask myself what two numbers multiply to negative 8 but add to positive 2. And just from a little trial and error, you could find that that's positive 4 and negative 2. Now, when I'm solving a quadratic and I factored, I can set both of these pieces equal to 0, and I should get two solutions. So, when x is equal to negative 4, that would make the denominator equal to 0, and when x is equal to positive 2, the denominator would also equal 0. You could always double check and just plug both of these back into that trinomial right there, and you'll notice in both cases you get 0. For number 2, express the following in simplest form. Now there's a lot of factoring in this unit. When I see something like this, I notice that the numerator looks to be factorable and that denominator looks to be factorable as well. So let's start with the numerator. That looks a little bit easier to deal with. Jumps out to me already that there's definitely a GCF of 7 because 49 is also divisible by 7, but they also have an x in common between the two of them. So if I divide that out, I'd be left with x minus 7. And you could always double check and just redistribute in to make sure you get that 7x squared minus 49x. But this is what the numerator would factor into. Now let's see what the denominator would factor into. 2x squared minus 13x minus 7. Well, I can't use the AM method like I did in the last one because I've got a leading coefficient. So this would lead me to use the AC method, where I multiply 2 and negative 7 to get negative 14. And I want to think of numbers that multiply to negative 14, but add to that negative 13 in the middle. Well, I know 7 and 2 probably isn't going to help me, but if I choose negative 14 and positive 1, those sum to negative 13. So the strategy is I'm going to split that middle term up. I'll bring down the 2x squared. And I'll make minus 13x plus 1x and a minus 14x, so that it doesn't change the value, right? If I combine those two terms, I'd get negative 13x. But it separated it so it factors nicely by grouping. Now, you could swap the order of these terms as well, and it wouldn't matter. You'll still end up with the same two binomials when you factor, just in a different order. So now I'm at the factor by grouping step. I could look at the first two terms and the second two terms, pull out a GCF from both of them. Between 2x squared and 1x, all they have in common is an x. And if I factor that out, I'd be left with 2x plus 1. Between negative 14 and negative 7, they definitely have a 7 in common. But in order to make the next set of parentheses match, I'm going to pull out a negative 7 so that I'm left with 2x plus 1 in the parentheses, such that if I distribute back in, I'd get that negative 14x minus 7. So you could do that at every step of the way just to make sure you're factoring correctly. Now, provided you factored by grouping correctly, that binomial should be the same between them. So I could pull out a 2x plus 1, and all I'd be left with is x and a minus 7. So that's what the denominator would factor into here. So really, this rational expression would be the same as if I wrote 7x times x minus 7 divided by 2x plus 1 times x minus 7. Now, usually when we're expressing in simplest form, when we factor, there should be something that reduces. And I notice I've got an x minus 7 in the numerator and in the denominator. So if I divide anything by itself, it just reduces to 1. So all I'd be left with, I've got a 7x in the numerator and a 2x plus 1 in the denominator. So there's nothing more I could factor. There's not a GCF in the denominator. That's as far as I can go there. If that plus 1 wasn't there, maybe I could cancel an x. But when things are linked by addition or subtraction instead of multiplication, there's nothing we could do there. Number 3, to solve that equation there, Ren multiplied both sides by the least common denominator, and I want to know which statement is true. Well, it's probably easiest just to solve this equation the best that I can. And when we're solving equations, we first want to identify what the least common denominator should be between all 3 of my terms here. So I'm going to take some time just to factor that first denominator. Instead of x squared minus 2x, I'm going to think about that as x times x minus 2. And if I'm thinking about it that way, I can get that x to look like x times x minus 2 if I multiply it by x minus 2 in both the numerator and the denominator. And I could also get the x minus 2 to look like x times x minus 2 if I multiply by x in the numerator and denominator. So my least common denominator here is x times x minus 2. So let's say I do that. There's nothing I need to do to the third fraction, but for 2x times x, I would just be left with 2x squared in the numerator there. And the denominator is just x times x minus 2. You could distribute it out, but I know I'm going to get rid of it in a minute anyway, so I could leave it in factored form. Minus, if I distribute that 11 to the x and to the minus 2, that would be 11x minus 22, all over x times x minus 2. And there's nothing I need to do to that third fraction there, because that already has the denominator that I'm looking for. So in this instance, all of my denominators are the same. So I can look at an equivalent equation by just looking at the numerators. There's one thing you need to watch out for here, and it's anytime you're subtracting. That I am subtracting an 11x, but I'm also subtracting a negative 22. So you could think about that negative as being distributed to both the 11 and the minus 22. So that when I make an equivalent equation with my numerators, I've got a 2x squared minus 11x plus 22, right? A negative times a negative is positive. The reason I say you really need to be careful here is because this is another quadratic, and really, when we get down to it, it should end up with something factorable. And the problem is, if you leave that as a minus 22, what you end up with will not be factorable and you'll get stuck. So every quadratic that you solve with these rational equations should be nicely factorable by the end of it. But the strategy remains the same. Get one side equal to 0 and see how much we can factor. So I've got 2x squared minus 11x plus 14 equals 0. Now, this again looks like another AC method because I've got a leading coefficient that's not 1, it's 2. So the strategy again, I'll take the 2 and the positive 14 and I'll multiply them. And I want to think of numbers that multiply to 28 but add to a negative 11. Well, if they're adding to a negative number, I know they both need to be negative to multiply to a positive. And the only pair that really comes to mind that gets close is negative 7 and negative 4. Those add to negative 11. So I can split my middle term again. We write it as 2x squared minus 4x minus 7x. Again, it doesn't matter what order you write those in. You could write them in any order. And remember, this is still an equation, right? So at some point I want to solve for x, so all of this is still equal to 0. Once I have 4 terms, I'm going to treat it like a grouping problem, pulling out a GCF from the first 2 and a GCF from the next 2. So 2x times x minus 2 and a minus 7 times x minus 2 again. Again, you want to pull out something so that your sets of parentheses match in both cases. Now, I could pull out an x minus 2 from both of these, and I'm left with x minus 2 times 2x minus 7 equals 0. So I'm going to give myself just a little bit more room here. And once I factor, I could set both of my factors equal to 0 and get 2 solutions for x. So I'll set x minus 2 equal to 0 and 2x minus 7 equal to 0. Usually when you factor by the AC method, you'll end up with one solution that's not an integer, or that's some sort of fraction. So I get x equals 2. And if I solve my other mini equation over here, divide out the 2, divide out the 2, I get x equals 7/2. So I get x equals 7/2, and I get x equals 2. But when you're solving a rational equation, you always want to have this extra thought in your head of, do any of these cause an issue for me when I substitute back into that original equation? And really, it's any value that would make any one of the denominators equal to 0, because if I've got some number divided by 0, that's undefined, so that would not be a solution to this equation because it wouldn't make sense when I plug it back in. And I notice for that first denominator, if I substitute in x equals 2 as a solution, this first part would look like this. 2 times 2 is 4, and 2 minus 2 is 0. So that would be undefined, and as such, I can include x equals 2 in my solution set. So even though I got it, like from the algebra that we did, I'd have to reject it because it doesn't make sense when I plug it back into the solution, into the original equation, and that's called an extraneous solution. So if you plug 7/2 back in, it doesn't look like it's going to cause an issue there. If I did get 0 as a solution, that would be an extraneous solution, but I didn't get 0 when I solved it. So the only answer choice that makes sense here is answer choice 1. 2 is an extraneous solution. It's something that I get as a solution when I solve algebraically. When I plug it back in, it makes at least one of the fractions undefined. Now, for both of these equations, it could be the case that we get extraneous solutions, and it could be the case that we don't. It really just depends on how the numbers work out. So for part A, we still want to identify an LCD, and if you're not sure what it is, a quick trick is to just multiply the denominators that you do see, because I can get all of them to look like x times x plus 3 pretty easily. I can multiply the first fraction by x plus 3 over x plus 3. Again, I need to do it to the numerator and denominator because x plus 3 over x plus 3 is just a fancy way to write 1, and I could always multiply something by 1 without changing the value. For x plus 3, I can multiply by x over x and x over x as well. So if I distribute that 2 in there, in my first numerator, I'd be left with 2x plus 6 divided by x times x plus 3 minus 3x squared times x plus 3 equals x squared times x plus 3. Now all of these have the same denominators, so I could look at an equivalent equation with just the numerators. I don't have to worry about that distributing the negative that I did in the last problem because there's only one term that I'm subtracting there, so it's only if I'm subtracting more than one term that I really need to stress about that. But this is another quadratic, and my strategy is get one side equal to 0 and factor as much as I can. Now, I tend to like my x squared terms to be positive. It's just easier for me to think about it that way. So I'm going to add that 3x squared over to both sides, even though I'm going to have to move 3 terms over rather than just moving the x squared to the left-hand side. But still not that much work. I'd be left with 0 on one side. 1x squared plus 3x squareds would be 4x squareds, minus a 2x, and minus a 6. Now, this looks like it's probably going to be an AC method, but remember, the first kind of factoring we should always look for, regardless of where we are, is a GCF. And it looks like all of these terms are even, so they're divisible by 2. So I'm just going to start by dividing everything by 2 to make the numbers a little bit smaller to work with. And I'm left with 2x squared minus x minus 3, which, while it'll still be an AC method, the numbers are at least a little bit smaller to work with. So again, 2 times negative 3 is negative 6. I want to find two numbers that multiply to negative 6, but add to negative 1. That's negative 3 and 2. Again, you could do a little bit of guess and check there and just add pairs of numbers that multiply to negative 6 and wait until you get negative 1. That's not a bad strategy to do that. And I'm going to split that into plus 2x minus 3x minus 3. Again, it doesn't matter what order you write those two terms in. It'll still factor nicely either way. If I pull out a GCF, I can take out a 2x from my first 2 to be left with x plus 1. And I could pull out a negative 3 from my next 2 to still be left with x plus 1. So altogether, when I'm done factoring this, I've got a 2 that I pulled out initially. I've got an x plus 1. And I've got a 2x minus 3 as well. Looks like I ran out of room yet again. So let me just give myself a little bit more room here. And I'll keep going. I'm going to split it off and set each of my factors equal to 0 to find values of x that satisfy this equation. Now obviously 2 is never going to be equal to 0, so I don't need to worry about him. But x plus 1 could be equal to 0. And 2x minus 3 could also be equal to 0. If I subtract 1 on both sides of the equal sign here, I find x equals negative 1. And if I add 3 to undo the minus 3 and divide by 2, I find that x could also be equal to 3/2. Now I just want to double check and make sure, just by looking at the equation, that neither of these are extraneous. And it looks to me like it's okay. If I had like x equals negative 3 as a solution, that would be a problem because the x plus 3 would be 0. Or if I had x equals 0 as a solution, that would make the first fraction have a denominator equal to 0, and that would be undefined. But I got negative 1 and 3/2, so both of those work out when I plug them back in. Now, not every equation that you end up with will end in a quadratic. In this case, one of my terms doesn't even have a denominator, right? So it's like, that's just 2 over 1. 2 of them are already x minus 3. So I can assume the least common denominator here is x minus 3, because I can just multiply that 2 by x minus 3, divided by x minus 3, and all of them would have the same denominator, right? I'd have 4x over x minus 3 equals 2x minus 6 over x minus 3 plus 12. Over x minus 3. I just distributed the 2 into there. Again, once all of my denominators are the same, I could rewrite an equivalent equation with just my numerator and solve this, right? Negative 6 plus 12, those are like terms I can combine to get just 6. And if I minus 2x on both sides, I get 2x equals 6, or if I divide out the 2, x equals 3. So really that one wasn't that bad, right? Until I go back to look at the original equation. And I think about, oh, well, wait a minute, right? My denominator for 2 of these fractions originally is x minus 3. So if I substitute in 3 for an x value, I'd have 0 in the denominator, which is a big problem, right? That part would be undefined. So I actually can't accept 3 is a solution here. I'd have to reject it because it's extraneous. So if I'm trying to write a solution for this equation, there is none. So I could just write no solution. So sometimes that'll happen, right? This wasn't a quadratic where I got 2 answers and one of them worked and one of them didn't. I only got one answer. When I plugged it back in, it didn't work. Therefore, there must be no solution to this equation. Number 6, perform the indicated operation and simplify completely. So you need to be a factor master to be able to do these sorts of problems quickly. When you're multiplying 2 fractions, the first thing you could do is factor everything that you see and cancel anything that you have in common. So for x squared minus 1, that's a difference of 2 squares, right? Dots. That factors into x plus 1 times x minus 1. That first denominator looks like a regular AM method, right? What adds to 5 multiplies to 4. Well, it's either 2 and 2, but that adds to 4. So I guess 4 and 1 would be the other pair. X squared in that second numerator, nothing I can do with, but in that denominator, looks like there's a GCF of x that I can divide out. And now I'm looking at my numerators and denominators, and I want to see what I can reduce. X plus 1 divided by x plus 1 is just 1. x minus 1 divided by x minus 1 is just 1 as well. And I notice that I have an x and an x squared. And both of these guys can be divided by x. If I divide x by x, I just get 1. But if I divide x squared by x, I get 1x still. So it's like I've got 2 x's in the numerator, 1 in the denominator, but I've still got 1 hanging out in the numerator once I cancel. So as a final answer, the only thing I have left in the numerator as I'm trying to multiply things across, I just have a bunch of 1s. And that x that reduced from the x squared. And in the denominator, all I have is x plus 4. So a lot of the times when you're multiplying or dividing rational expressions, after you factor, there will be at least a few things that reduce to 1 so that your answer cleans up pretty nicely. When you're dividing for something like b, the only extra thought you have to have is that you need to keep the first fraction, change the sign from division to multiplication, and flip the second fraction. So really the problem we're going to be looking at is negative x squared plus x plus 20 divided by 5x squared minus 25x times 2x minus 14 over x plus 4. And then all the same rules apply. I want to factor as much as I can and then see what reduces. Now it looks to me like that guy factors pretty nicely with the greatest common factor. So does that denominator right there. Both the 5x squared and the 25x have a 5x in common. Nothing I can do with x plus 4, but this trinomial looks like it would be pretty good to factor if that leading coefficient was just 1. So I'm actually going to rewrite it to make it easier to think about. Instead of having a negative out in front, I'm going to factor out a negative 1 from all 3 of those terms. Essentially, the effect that has is flipping the signs of each of my terms, such that if I distribute that negative 1 back in, I'd get negative x squared plus x plus 20. The reason I did that is because it's a little bit easier to factor, since I could just think about this as an AM method. Numbers that multiply to negative 20 but add to negative 1. So I'm going to rewrite that down here a little bit cleaner. I pulled out that negative 1. And numbers that multiply to negative 20 but add to negative 1 would just be negative 5 and positive 4. In this first denominator, when I factored out the 5x, I had 5x times x minus 5. And I was left with something like this. And again, there should usually be a couple things that reduce nicely. I notice in the numerator, in the denominator, I have an x minus 5. That would reduce to 1. And I've got an x plus 4. And an x plus 4, that reduces to 1 as well. So if I multiply everything I have left in my numerator, I've got a negative 1 times 2, which would just be negative 2, times x minus 7. And all I have in my denominator is a 5x. So that's as far as I'd be able to simplify that, right? Negative 2 and 5 don't have anything in common, and there's nothing I could reduce that x with. So sometimes your answers will be really clean and a lot of things will simplify, but sometimes you'll be left with a binomial or two. It just depends on how the factoring goes. Now when you're adding or subtracting fractions, you've got to make sure you've got a like denominator before you can do that, right? If I add 1/5 plus 2/5, easy peasy, right? 3/5. But if I asked you to find 1/5 plus 2/8, all of a sudden you would need to think a little bit to get a common denominator. So in this instance, they've got common denominators already, so I'm just going to combine the numerators. I'm going to minus that 8 from the 4 to be left with 4x to the 4th minus 4 when I do positive 4 minus 8 over x squared plus 1. And after we combine, usually there's something that we could factor and simplify a little bit better. So that numerator definitely has a GCF of 4 I could pull out to be left with x to the 4th minus 1. And now I also notice that x to the 4th is a perfect square. That's just x squared squared. And 1 is also a perfect square, right? That's just 1 squared. So technically that x to the 4th minus 1 can be factored further as a difference of 2 squares. I could write it as x squared plus 1 times x squared minus 1. Which is pretty nice given what my denominator is, because I notice I have an x squared plus 1 in the numerator and the denominator. So I can reduce that to 1, and all I have is a 1 left in the denominator, so I don't even need to write it. And in the numerator I've got a 4 times an x squared minus 1. Now even if I wanted to factor further, yes, this is still a difference of 2 squares. So if I wanted to write my answer like this, that would be acceptable as well. In an instance where I don't have common denominators, I want to factor all the denominators that I have and then figure out an LCD before I can combine them. So that 9x squared minus 4x, that to me looks like a difference of 2 squares as well. If I multiply 3x and 3x, I'd get 9x squared. And if I multiply a 2 and a minus 2, I'd get negative 4. So really that first denominator is the same thing as 3x plus 2 times 3x minus 2. The numerator is negative 3. And my second denominator looks like all there is a GCF of x there, where I could factor out an x, and I'd be left with 3x plus 2. So in my first denominator, I would need a lone x by itself that I could multiply by, because I know I have this x in the second denominator. So my LCD needs to have an x, but it would also need to have a 3x plus 2 and a 3x minus 2. So 3x plus 2 and 3x minus 2. And I can definitely get both of my denominators to look like that. So in my first fraction, to get the denominator to look like that, I can just multiply by x over x. And I'd be left with negative 3x over x times 3x plus 2 times 3x minus 2. And in my second fraction, the only piece that I'm missing is that 3x minus 2 that I can multiply by in the numerator and the denominator. If I do that, I'd have a 3x minus 2 times 1, which is just 3x minus 2, over x times 3x plus 2 times 3x minus 2. Now you'll notice these denominators are the same, so I can combine them into one fraction and just add the numerators. And the good news here is there ends up not being a lot to simplify when you combine them. I noticed that negative 3x plus positive 3x is just 0, so all I'd have left in the numerator is negative 2. And there's nothing I could factor in the numerator, it's just a negative 2 hanging out, so there's nothing I could cancel from there. For the last question, it asks to factor completely 8 minus 27x cubed. Well, if it's two terms, sometimes it's dots, right? A difference of 2 squares. But 8's not a perfect square, 27's not a perfect square. So this is probably one of those SOAP problems, or a sum of difference of cubes. If you remember the formula for that, a cubed minus b cubed, that's the first thing minus the second thing, times a squared, plus ab, plus b squared. Now the way I remember the signs is that my first sign is always the same as what I started with, the second sign is opposite, and the last sign is always positive. That's what I mean when I say this is a SOAP problem. So I need to identify my a and my b. Your a is the first thing that you're cubing, and you can guess and check, but if I cube 2, I would get 8. The next thing I want to think about is, what would I have to cube to get 27x cubed? Well, 3 times 3 times 3 is 27, and x times x times x is x cubed. So the a that I'm going to plug into that formula is 2, and the b that I'm going to plug in is 3x. So when I make those substitutions, it'd be 2 minus 3x times 3x squared plus 2 times 3x, which would just be 6x. Oh, excuse me, that should be the a squared, right? So that's just a 4 out in front. But the 3x squared is that b squared at the end. Now there's a reason why I'm leaving it like that, because you're squaring all of b in that last term there, which means it'd be a problem if I just wrote it as 3x squared, because that's not what I'm squaring. I'm squaring the x, yeah, but I'm also squaring the coefficient of 3. So when you write your final answer, especially if this is like a multiple choice question or something, make sure that that coefficient is squared as well as the variable.